So the first thing is, let me tell you. So you might have received an email from the exam office regarding the mid-sem exam, right?
Yes, sir.
Yes, sir.
Yes, sir.
And so the exam will be conducted on, whatever the exam office has circulated, and as per the time and table. And regarding the exam pattern as well as syllabus, right?
Yes, sir.
Yes, sir.
Yes, sir.
So the exam pattern, so far, we have not, received any information from the exam office. And previously, the mid-sem exam we used to conduct by through multiple choice questions. Okay. Most probably there will be such multiple choice questions, or maybe some subjective type. Okay, so as soon as I got this message from as soon as I get this message from the exam office, I will circulate to you. Okay,
Yes, sir.
is it clear? But most probably multiple choice questions. Okay, we can split into two we can split into two exams, like 15 marks, 15 marks, therefore 30 marks. Okay, and that will be conducted on that day only. Okay, so let me first check with the exam office, and the details I'll circulate. Is it
And
clear?
sir,
Sir, you have given us the due date of physics assignment on 12th of February. Sir, can you please extend it because our exams will be ending on 11th of February?
Okay, that I will do. Okay, so that I'll do. Don't worry, that I will do. Let me do right now.
And sir, also with the lab experiment as well.
Okay, so these things also I'll do. Okay, don't worry.
Thank you,
and
sir.
sir, about the syllabus, whatever has
So
been covered till date,
mm,
that will be there.
just a moment. So it was February 12. Should I make it 15? Will it be okay? 15
Yes, sir.
February will be okay?
Yes, sir.
Is
Yes,
it
sir.
okay?
Yes, sir.
So let's make to 15 February. Okay.
Yes, sir.
Answer that of physics virtual lab experiment.
Sorry, your voice is breaking very heavily.
Sir,
Satyush.
sir,
Yes.
about the virtual lab, physics virtual lab experiment, can you extend that too?
That I also do it. Let me check with our lab demonstrator, Mr. Murtanji, and after that I'll do. Okay. And regarding the syllabus, right? Don't worry about syllabus. Whatever I am teaching, you just read those things. I have already, clarified regarding this matter. So you'll get small problem based on your assignments, and as well as based on your whatever I'm teaching. If it will be your subjective type, and if it's subjective type, again it must be based on my teaching, right? It should not be beyond my teaching. Got it?
Yes, sir. Yes, sir.
And
Yes,
whatever I
sir.
am teaching so far, okay? The lecture notes, video lectures. Unfortunately, today I might not record because the same problem persists. By the lecture notes, some of video lectures I have already uploaded. You can revise them, then that will be okay. Okay.
Okay, sir.
Yes, sir.
Uh, um, so let's start today's lecture. When your exam is starting?
9th.
9th.
9th
Sir,
means which day, if I ask?
sir,
So Wednesday.
Wednesday.
Wednesday. Wednesday.
Wednesday. Okay. Is my screen visible to all of you?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
And since on Wednesday there is exam, we should not have class on coming week. Okay. Am I correct? Or should we have a class on Monday, the coming Monday?
So we shouldn't.
Okay. So let's
Okay.
okay, try to cover whatever we can do in this week. Okay. So everybody, please go to mute mode. Everyone. Okay. So today we will be discussing entirely new subject or branch of physics known as quantum physics. So whatever you have learned so far, right? Even if you beginning from your high school, so those are based on classical physics. That means so they follow Newtonian mechanics. That means Newton's law. When you say Newton's law, it basically indicates the second law of Newton's. Okay, the rate of change of momentum equal to applied force. dp over dt equal to force. So the quantum physics, um, you might have heard about photoelectric effect. Yes or no? Have you heard about photoelectric effect?
Yes,
Yes,
sir.
sir.
So then photoelectric effect. So some of the notable physicists or you can say scientists, they did a very hard attempt to explain the observation of the photoelectric effect. However, they could not explain successfully. Okay. So, but Einstein used a theory. When you say theory, it's basically, I mean, use the concept of photon. Photon, everybody knows. It's instead of treating light as a wave, you should treat light as a particle. Okay. So light as a particle which has energy equal to h nu, where h is Planck constant, nu represents frequency. Okay, so Einstein used the concept of photon and he successfully explained the observed, whatever one can observe from the photoelectric effect. And for this, the great Einstein won Nobel Prize in 1921. Okay, so so therefore there are also other things like black body radiation. Okay, so the black body radiation. So it means one in principle one can so everybody knows about black body radiation.
Yes,
Yes or
sir.
no?
Yes, sir.
Yes, sir.
And
Yes, sir.
on a very good video lectures will be available on YouTube, and even with search you'll get all those things. Okay, so these things the photoelectric effect, black body radiation, I'll put as a self study. Okay, so you please read those things. Let me tell very briefly what happened black body radiations. Okay, so in black body radiation, so one can so it's like we have you can prepare in principle, take a spherical hollow spherical objects, and in the inner part you put black color, because black color will reflect almost everything, right? And you make a small hole, very narrow hole, and incident the light, and there is a very less probability that light can escape from this. Let me show you black body radiation. If I type, okay, okay, this is the black body radiation spectrum. You can it's a spherical black body spherical object. Let's say. Let me search. So you can find so like here you can see it, right? So this one, do you able to see?
Yes, sir.
Anyone with this figure? So you
Yes,
can
sir.
see, right? So you incident the radiation. So there is a very less probability that light can escape from this, chamber. And what will happen at certain temperature? One will, observe that this object will radiate a different spectrum. When a spectrum frequency, different frequency of the radiations. Okay, so you can see it's small. So this is typical. One can prepare a black body in laboratory. Okay, so one should observe various radiation. And the classic example one can have that if you heat a piece of iron rod, if you increase the temperature, it will become, first, red color, then yellow color, and then white color. Okay, like here you can see, right? So this, okay, like piece temperature by color for glow, right? So you can see. So you can see these things. But what I would like to, bring your attention here. So here, what we'll have that the spectrum, that means the frequency. Sorry, here the energy density. So when you say energy density, energy radiated per unit area or a unit volume per unit second, called energy density. The energy density versus frequency, right? And you can see these are various temperature. Do you able to hear me? Yes or no?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So you can see this is 30 degree, 3000 Kelvin, 4000 Kelvin, 6000 Kelvin. Okay. So this is the observed things from a black body radiation. It is called black body spectrum. Okay. So various, as I said, various physicists, for example, Rayleigh right, Wien's, and you can see, you can study, right, Wien's radiation formula, Rayleigh displacement law, Rayleigh formula, and so on. Okay, so they, even with Stefan's Boltzmann law, right? So they used various, they actually put a lot of effort to explain this phenomenon. However, they could not able to explain why the spectrum is like this. Okay, how the why the energy radiation increases as you increase temperature, and why there will be, if the frequency increases, it will increase, and if you further increase frequency or decrease wave, if you further increase the wavelength or decrease frequency, so then the energy density will decrease. Why this, right? So, for example, if someone believes, let's say, Rayleigh formula, it says, when we say by increasing frequency, that means it is equivalent to decrease wavelength, because frequency and wavelength, they are related by a reciprocal relation. Okay, lambda, because the one can get frequency from the velocity and as well as wavelength. So one can see, if you keep increasing frequency, that means if you decrease wavelength, then the energy density in principle increases. Okay, and when frequency goes to infinite, in principle the energy density will be infinite, but that is not the case. Okay, so if the frequency goes, very large, that means wavelength 0, then the energy density is 0. So nobody able to explain why it's happening. Right, as I said, Stephen Boltzmann law, you can see here, then Wien's displacement law, even the Wien's radiation formula, Rayleigh formula, they do able to explain, some of the observation, not all. And that effect called ultraviolet catastrophe. That means that in principle it goes to, infinite, right? And but one has to observe these kind of things, and that I was first theoretically explained by Rayleigh's ultraviolet catastrophe. Okay, so but what, Planck, so he used again the concept of photon. In fact, one of the statistical distribution called Bose-Einstein distribution, that we'll study in statistical subject. Okay, so for the time being, you don't trace yourself, just remember one of the distribution functions, and there he uses the concept of photon. Okay, and that Planck constant that everybody knows was actually because of this Planck. Okay, so Planck successfully explained these things. Why the black body spectrum is like this. As I said, the details you can study yourself. The black body radiation. Okay, so the basic things are the brief things I have told you. Okay, and similarly photoelectric effect. Everybody knows. Yes or no? Photoelectric effect.
Yes,
Yes,
sir.
sir. Yes, sir.
And
Yes, sir.
again, I will suggest you read yourself, right? So how the classical physics does not able to explain some of the notable observation of photoelectric effect. One of the important thing is that if you do you remember photoelectric effect? So if you increase the frequency, right? So let me give this thing. So if you increase the intensity, right, by keeping the frequency below the threshold, then you should not observe any the current. But in principle, if the intensity will be more, then it can knock out more electrons from the surface of the photoelectric plate. Therefore, in principle, one can get large current according to classical physics, but that is not true. Okay, so what Einstein actually suggests or used in his theory, so taking the concept of photon, that means rather than considering the it's like a wave, like, so we should treat it as a particle which has frequency h nu. Okay, so therefore all the puzzles, okay, the discrepancies are solved by using the concept of photon. So so keeping all these small things, if somebody will ask you question, so that why basically we need the quantum physics. As I said, because the in some cases classical physics does not able to explain the observed phenomena. So therefore, one thought some alternative approach, that is therefore the quantum physics took part. Okay, so 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 here therefore I have asked these simple three questions, right? So if we answer or understand the meaning of these three questions or answer of these three questions, it means we will understand the basic principle of quantum physics. Now, why the quantum physics we need? Okay, so the first question is why we need quantum physics. That I have already answered, because the failure of classical physics to explain some of the observed phenomena. For example, the photoelectric effect, black body radiation, and so on. And the second question is, what is quantum physics? Although we understand that in photoelectric effect, we need to use some alternative approach rather than using the classical or Newtonian mechanics. As you know, Einstein used in photoelectric effect, Planck's used in black body radiation, and they successfully explained the observed phenomena. Okay, but what is that actually? Can we develop theory for quantum physics? Like, in classical physics, we have a theory. So similarly, in quantum physics, can we develop a theory? In alternative way, we can ask ourselves, what is quantum physics? And then the last question here is, where one can apply quantum physics in general. We know, the photoelectric effect case, we can apply, black body radiation case, we can apply. But in general, where one can apply quantum physics. So if we answer or understand these three questions, why, what, and where, it means we can understand some of the basic principle behind quantum physics. So let us discuss one by one. Am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, and whatever I am going to teach under the in this quantum topics, all these things will get from this in Arthur Weiser book. You go through, okay. So you go through the syllabus, you'll find one of this book, you'll find this book, okay, from your syllabus. Okay, so let's, discuss one by one. So here I would prefer to explain or, discuss in reverse way. That means first we'll see where one can apply quantum physics, and then what is quantum physics, and then the lastly where quantum physics. Okay, so the quantum physics is applicable to microscopic objects or world. So do remember, this is summary of of many things. Okay, so if you read a lot of books based on quantum physics, even the referred book as Arthur Weiser will conclude all those things. So it means the quantum physics is only applicable to small objects that belongs to some called microscopic world. Then you might ask questions. So what are the other type of objects? Basically, there are two different type of objects. One is called microscopic objects, another is called macroscopic objects. Okay. So then we can characterize these macroscopic and microscopic objects by objects based on the observed phenomena. For examples, if someone can observe the objects or phenomena associated with that object through naked eye, that means rather instead of using any instrumental help, then we can call they belongs to macroscopic world. And if the objects or phenomena produced by that object not observable by naked eye, then we can call or declare the object belongs to microscopic world. Got it? Yes or no?
Yes, sir.
Yes, sir.
For example, like people we can see around, bus, train, car, even if it's sun, earth, stars, planet, etc. Some of you may make argument that the planets like distant planets, we do not able to see our naked eye because they are very far away, but we know that they are exist, they are actually very large. Okay, so therefore it is naturally to ask, is there any length scale one can say these objects belong to microscopic world and other objects belongs to macroscopic world? Yes, there is a length scale, and that length scale is called angstrom, which is 10 to power minus 10. So if you look, electrons, proton, photon, atom, molecules, they belongs to microscopic world because we can neither observe objects or some of the phenomenon produced by these objects by naked eyes. As I said, that although we can not see some of the objects, for example, planets, but they are really belongs to macroscopic world. Therefore, in general, we have a length scale. So if the length, for example, if the dimension D represents the dimension of the systems is order of millimeter, then we can see through our naked eye. Therefore, we can declare they belongs to macroscopic world. And then, as we know, the electrons, proton, photon, their dimension is order of 10 to power minus 10 meter or order of angstrom. So there is a length scale, okay? And as I said, the Newton's laws are applicable, or Newtonian mechanics or classical physics applicable to macroscopic objects, whereas one cannot apply Newtonian mechanics on microscopic objects. So what does Newtonian mechanics says, or the Newton's second law says? It says if somehow we know the position and momentum at a given instant of time, then by using Newton's second law, we can precisely measure both position and momentum in the next instant of time without any error. So it's a differential equation, right? dp over dt equal to the force, right? And then if somebody knows the position and the linear momentum at a given instant of time, mathematical language the initial value problem, then definitely you can determine the position of momentum in the next instant of time. So that is precisely. Okay, but in for microscopic objects, forget about to get the information in the next instant of time. This a pair. They are called canonical pair. Okay, because the momentum and position, they are related. Like energy and time, they are related. So x and px, forget about to measure in the next instant of time. So for microscopic world, one cannot precisely measure both position and momentum simultaneously with 100% accuracy. There must be some error in the measurement. And this is which famous principle? This is uncertainty principle proposed by Heisenberg. Yes or no?
Yes, sir.
Yes, sir.
So we can see that how the Newtonian mechanics does not applicable to microscopic world. Okay, and so now we understand more or less about macroscopy and microscopic world, and quantum physics is applicable to microscopic world. Okay, and here is a schematic diagram in order to represent length scale. So here the left side, so this is our less angstrom. The here the boundary, you can say, if the length scale below these things, then it's called microscopic world. If the length scale more, that is called macroscopic world. Okay, and in summary, what we learn that quantum physics is applicable to those objects whose dimension is order of angstrom. Okay, is this clear to everybody?
Yes, sir.
Yes, sir.
Yes, sir.
So now we understand where we will apply quantum physics. Then the second question is, what is quantum physics? Again, I would like to emphasize here, if you read a bunch of books based on quantum physics, including the Arthur Weiser book, you will conclude that going to much deeper or looking at the mathematical formulation. If somebody will ask you question, what is quantum physics? Qualitatively, can you define it? Then definitely you can define it by saying like this. It is a branch of physics which is of course applicable to microscopic world or objects based on these three principles. What are these three principles? One is called wave-particle duality, proposed by de Broglie. The second one is the uncertainty principle proposed by Heisenberg, and the second one is a quantization of energy. You can say, the Planck's, proposed by Planck's, okay, or something like that, okay. And in fact, this quantization of energy is the consequence of the uncertainty principle that will also derive or prove, okay. So, but I would like to make it this list, because if you look any quantum mechanical problem or system, the first information you will get the quantization of energy. Okay, so I'll talk about what is the meaning of quantization of energy. So therefore, I have listed this one. So in short, like the wave particle duality, the uncertainty principle are like two legs of quantum physics. Okay, and quantization of energy, as I said, the consequence of the uncertainty principle that will describe. So by simply saying this, nobody will believe, right? So in fact, when de Broglie first proposed this wave particle duality, nobody believed, but they said we need mathematical formulation is okay, but there must be some experimental evidence. Remember, so for this work, every physicist got Nobel Prize. Okay, so let's first look one by one. What does wave particle duality says? As I said, proposed by de Broglie, and that time it was known as de Broglie hypothesis. And as I said, experimentally proved. We will also discuss. And for this wave particle duality, theory, okay, um, um, the de Broglie won the Nobel Prize in 1929. Okay. Am I audible?
Yes, sir.
Yes, sir, audible.
So everybody knows one of the great physicists, Indian physicist, also won the Nobel Prize. So who was that?
Sir C.V. Raman.
C.V. Raman.
Sir
And
C.V.
when
Raman.
he received the Nobel Prize, won the Nobel Prize?
Raman effect.
Effect.
Raman effect. So in which year do you remember? Anybody? 1930.
1930. 1929. I think. Or
Hmm?
1929.
19, not
1930.
1930. But do you know that the Nobel Committee has proposed Raman name in 1929 for the Nobel Prize? Everything was on the table. But this groundbreaking work by the De Broglie, so the Nobel Committee decided to give Nobel Prize to De Broglie in 1929 and Raman in the next year. Okay, so you can realize what the potential work by the De Broglie, right? So immediately proposal came, and because everything proved. Okay, so in mathematical language, lambda equal to h over p. I'll discuss in a great detail, although some of you might or all of you already knew, right? Lambda represents the wavelength, h is the Planck constant, p is the linear momentum associated with the particle. Okay. So what does wave particle duality means? It means the microscopic object, because of course it is applicable to microscopic objects. So microscopic objects behave as wave and also particle. I mean, it's strange, right? How come one will behave wave as well as particle? It depends on how one will observe it, depending on the observations. For example, let's look at some of the well-known particles. For example, electron. Electron, everybody knows is a particle, right? Because it's a dimension order of angstrom, so therefore it is a particle. So let's look at some experiments. There are experimental evidence where electron can behave as wave as well as particle. So the electron particle photoelectric effect, again 1921 Nobel Prize, Great Einstein. And the electron as a wave, there is scattering experiments. And that scattering experiment is a Davison-Germier experiment, which is actually proved the De Broglie hypothesis, the wave nature of the particle. And for this, Davison won the Nobel Prize in 1937. You can see the asterisk. But the Germier, which was also a very good physicist or scientist, did not win the Nobel Prize. Okay, and if you read the story behind it, there was again the politically debate, right? So they have some rivals in that Nobel Committee, and they said Davison has actually contributed, as Germier has no contributions. So the Davison won the Nobel Prize jointly with some other physicists, whereas Germier never won the Nobel Prize. Okay. So anyway, so as I said, the Nobel Prize for this. And then, so let's look at, a well-known wave, and let's see whether they will behave as particle or not. So light is a well-known for this wave nature. We have already studied Newton's rings experiment, diffraction, and so on, even polarization, by using the light as a wave, right? As I said, interference, diffraction, polarization, and so on. For the particle, they said the photoelectric effect. So you have to consider light as a photon, is a particle, in order to explain the observed phenomena from photoelectric effect. Okay, so in short, what we conclude that wave particle duality really exists, and it has been proved, experimentally. So there is no doubt at all on De Broglie hypothesis. So that time people were calling De Broglie hypothesis because it was hypothesis at that time. Nowadays, people can call it the de Broglie, principle or de Broglie rule or de Broglie theory, whatever you like. Okay. And the second leg of the quantum physics is the uncertainty principle proposed by Heisenberg. And in 1932, he also won the Nobel Prize. So the uncertainty principle again we'll study in a great detail with its some of the notable application. As I said, the quantization of the energy is one of them. So but here you can also look at this inequality relation, delta x delta px is greater or equal to h over 4 pi. What is delta x? If you measure the position and momentum at a given instant of time, so these are the error in the measurement, delta x, delta px. The error in the measurement of the position of the particle and the error in the measurement of the linear moment of the particle, x component of the linear momentum of the particle is related by this relation. And the uncertainty principle is actually proved the electron diffraction through a slit experiments. So we have studied single slit diffraction chapter, but here electron is a particle, it also get diffracted through a slit. And there if someone wants to measure even double slit experiments, again I can put is a self study. You'll find in a lot of good video lecture on YouTube, right? How come if one will try to measure the position, then the linear momentum uncertainty will be very high. If someone will measure the linear momentum through kinetic energy, the particle gets scattered over the screen and so on. So that really proves the truthness of the uncertainty principle, the existence of the uncertainty principle. Okay. So now, so the de Broglie hypothesis as well as uncertainty principle, they, in early 19th century, people were thinking, okay, so these are useless because there are no experimental evidence nowadays. Maybe after 100 years, even if because we are studying this theory now, so therefore we can say after 100 years we came to know that they are actually true. So the last one is a quantization of energy. That means the discrete energy level. So what does it mean? We have already got the energy of the simple harmonic oscillator, damped harmonic oscillator, post damped harmonic oscillator. And if I ask what is the energy distribution of the simple harmonic oscillator, then you can say let's say this is minus a plus a its amplitude, and then we'll have the kinetic energy will be like this, the potential energy distribution will be like this, and the total energy is constant. Okay, so here is energy equal to omega square a square, where is the amplitude. Okay, so and you can see there the energy is continuous, right? So it is not discrete, it's continuous. Because we have this relation, parabolic relation. Okay, so but what quantum physics says that we should not have this continuous energy system. We must have discrete energy level. In other words, the energy will be NH nu. What is N? N represents the energy level, and we can say the quantum index. And like in Newton's ring, N was representing the order of ring. So similarly here, N represents the quantum index, and the energy will be depending on the energy level, it will be NH. So like energy E1, E2, E3, E4, E5, E6, and so on. The energy will be like this. But in classical, we'll have energy will increase continuously, but here the discrete. Okay. And simply saying won't work, as I said. So we need experimental evidence, the Frank-Hodge experiments, right? Which proves the existence of discrete energy levels. And for this in 1925, Frank and Hodge both won the Nobel Prize. Okay, so as I said, for example, the classical simple harmonic oscillator, the energy is half m omega square a square, and if we will have quantum simple harmonic oscillator, the energy will be n plus half h cross omega. So this will derive later on. Okay, and you can see the energy will be half h cross omega. What is h bar? H bar is h over 2 pi, where h is the Planck constant. So is this clear to everybody? Am I still audible?
Yes, sir.
So now, if I ask you question, if you look these three ideas, whether the wave particle duality here, the mathematical expression, the uncertainty principle here, and this discrete energy level here, what you can see a common things here. Anybody can give answer? What is the common thing one can notice?
Duality of particle and as well as radiations.
So that's, we discussed here too, we discussed there are, particle as well as wave or radiations. But if you look this mathematical formula, what common thing you will observe? That all these mathematical expression,
Planck's
that
constant.
yes, the Planck constant H
Yes,
is
sir.
appearing here. So yes, the Planck constant one can say the heart of quantum physics. Okay, so the H, what is the value of H? Order of 10 to the power minus 34, 6.623 10 to the power minus 34. The order of magnitude 10 to the power minus 34. Okay, so Planck constant plays a crucial or very, very important role in quantum physics. Okay, and in the next class, we'll see how, Planck constant, the value, because the nature designed the Planck constant. Our universe designed the Planck constant for us. So we, the human being or observable object, never ever show their wave character. If you look at de Broglie hypothesis, all the material particle will have its wave nature through this relation lambda equal to h over pi. So P can be calculated. In fact, in the next class, we'll discuss in great detail about de Broglie hypothesis. There will also discuss, that where one can actually apply the quantum physics. We know that there is length scale, which is angstrom, which separates microscopic world. But how de Broglie hypothesis play an important role in quantum physics, that we'll also discuss. So here the wavelength associated with the material particle lambda, and if the lambda, the de Broglie wavelength associated with the material particle is comparable to the dimension of the system, okay, then the particle will show its wave nature. Otherwise, it won't show its wave nature. And there the Planck constant appear in the picture because the order of the magnitude of 10 to the power minus 34. So therefore, although if we calculate our linear momentum, assuming that we are moving a velocity, very fast velocity, let's say, we are sitting on a aircraft or rocket, we are moving very fast. And if you try to calculate our wavelength by using the Planck constant, and still it will be not comparable to the dimension of our system. So what is dimension of our system? You can say order of 1 meter, right? It's order of the magnitude. You measure from top to bottom or left to right shoulder. Okay, you can say order of meter, or you can say 0.5 meter order of magnitude. And if you compare the calculated de Broglie wavelength, then the magnitude will be very, very large. In fact, the D will be much, much greater than the computed de Broglie hypothesis. So therefore, we human being never ever show our wave nature. And if the nature, because of the Planck constant, as I said, and there will also work out very similar, very interesting problem. If the Planck constant will be 10 to the power, let's say minus 4, let's say some positive number, let's say order of the magnitude 1 rather than 10 to the power minus 34, then it might be true some other universe, right, where the material particle, like even the bigger object, they could also show their wave nature. Okay, you might have seen some Hollywood movies, interesting movies, like some of the superhuman, they can penetrate some barrier, right? Like they'll move like a wave. Probably for them, quantum physics is applicable. Okay, because they can show their wave as well as particle nature. Okay, so this is all about the elementary ideas of quantum physics. What we came to learn at the end of today's lecture, that quantum physics must be based on three important principles. Okay, one is de Broglie hypothesis, second one is uncertainty principle, and third one is the quantization of energy. And we have already discussed the first question, why we need quantum physics. Okay, so as I said, you can consider photoelectric effect, black body radiation. These two I will assign as a self-study. Okay, you'll study it and you may find some of the question in your exam. Okay, and because these are very elementary things and you have already gone through it, so therefore no need to discuss in a great detail. And similarly, the Frank-Horst experiments. Okay, or all those things. Okay, everything will get this book, Arthur Weiser. Probably I'll upload some of the portion and we'll read it.
Yes, sir.
Okay,
Yes, sir.
so in the next class, we'll discuss, as I said, the de Broglie hypothesis, and there we'll see what is the relation between the de Broglie wavelength and the dimension of a system, which case the object will show microscopic object will show wave nature, or which case it won't show. And then we'll discuss about the uncertainty principle. As I said, the quantization energy is the consequence of the uncertainty principle. That we'll also see in the next class. So any question so far?
Excuse me, sir.
Yes.
Sir, could you please explain once again that why we human beings cannot show wave nature?
Which one?
Sir, that part where you were telling that why we human beings can't show our wave nature.
So that we'll discuss in a great detail, next class. What I said that if you, because the de Broglie hypothesis says that one can calculate the wavelength that every material particle, that means the material particle which has matter, mass, right? So we can calculate in principle the corresponding wavelength called de Broglie wavelength. And how one can calculate? By using this principle. And if you calculate the de Broglie wavelength for a human being, assuming the Planck constant 10 to the power minus 34, not assuming, it's true, right? And assuming that man is sitting in a space rocket, which will move with the velocity 10 to the power, let's say 6 meter per second, or close to 10 to the power 8, velocity of light, right? And if you calculate, the mass of the human being is 100 kg. And if you calculate, and what will find that it is
Minus 44.
10 to the power 8, and then we have the Planck constant. It will be 10 to the power minus 34 into minus 42. Okay, the de Broglie wavelength. So, and what is the dimension of a human being? It is order of, let's say, meter. Okay, 10 to the power 1 or 10 to the power 0. So now it's 10 to the power minus 42 wavelength order of, the dimension is 10 to the power 0. So the d is much greater than there. So it is not comparable. So therefore, a being never ever show its wave nature. So that's that I wanted to tell you. And these things we'll discuss in a great detail in the next class, as I say. Okay.
Okay, sir.
Yes, sir.
I would like to repeat. So if you read all the quantum physics, and at the end we'll conclude. So these things, right? So why we need quantum physics? That indicates the failure of the classical physics. As I said, photoelectric black body radiation, even if Compton scattering, if someone is interested, they can also study this. And then the second question is, what is quantum physics? As I said, it must be based on three simple ideas: de Broglie hypothesis, uncertainty principle, and quantization of energy. And the next question is, where one can apply quantum physics? As I said, applicable to microscopic world. Okay. If there is no further question, I think we should stop here and we'll meet in the next class to discuss
Sir,
about de Broglie hypothesis as well as uncertainty principle.
sir, I had one query.
Yes.
Sir, will quantum mechanics come in mid-sem?
Yes. Okay.
Okay, sir.
Or we should not ask quantum physics.
No, sir, please don't.
Because quantum physics is a little bit tough and we need time to practice it, and it would be very soon if we just read them and go for the exam.
The photoelectric effect and black body radiation, you have to read it and these things. Okay. So assume that only unit 1, okay? Got it?
Okay. Yes, sir.
Okay, for the time being, you assume, no, for the time being, you assume whatever I covered, whatever I will cover till the end of this week, this will come your exam. But the same time, you can also assume only for first unit. Okay?
Okay, sir.
Got it?
Yes, sir. Thank you, sir.
Because I have to also ask my colleague, because they are also teaching different branches, how far they have gone. Okay? And whatever the minimum things we have covered for both branches, the question will be coming based on that. If some branches, someone has taught quantum physics, some branches, someone has not taught quantum physics, then it will be unfair to ask questions, right? So therefore, whatever the minimums, my colleague as well as, I have covered, then question will be coming based on that. So you assume only first unit, okay? Is this okay?
Okay, sir.
Okay, sir.
And as I said, whether multiple choice or subjective type, I'll check with the exam office and let you know. And if it's a multiple choice, we probably conduct in 2 sittings. That means maybe 15 minutes consecutive, right? We'll have 15 minutes, then again 15 minutes, back to back.
Okay, sir.
Okay, so bye everyone. We'll meet tomorrow.
Thank you, sir.
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 Thank you, sir.